Hey, welcome back to discussion 20. Now we are going to be doing problem 79, 80, and 81 in page 359. So we're given a large horizontal rod is fixed to a pole, and it's suspended by a rope at the end, so it looks something like this. So here's the large pole, and let's just use brown for the rope, right? Why not? So here we have the rope, and then here we have the rod. We'll call it the rod. Okay, so this is 30 degrees. We are told the rod itself is 1.75 meters long. And we want to know what is the magnitude of the torque exerted by the tension in the rope around the fixed end of the rod. So, in other words, what is the torque going this direction on the rod? So one of the easiest ways to look at this, in my opinion, is to consider a free body diagram. So we have this rod here, and this tension force. Okay, so this tension force is actually going to be, it's going to have a, it's pulling straight up, right? So it has two components. So this will be FTY. It also is pulling this direction along the rod, which is going to be FTX. So now we also have a normal force that's pushing from the pole against the rod itself, and this is going to be Fn. So naturally, these two are going to cancel out because there is nothing really happening in this direction, right? We also have a weight force. Let's move this over here. We also have a weight force coming down in the center of the mass of the rod. All right, so that's a pretty good starting point. Okay, so the reason it's useful to look at this in free body diagram form is because we're going to need to determine the torque, right, due to the tension force. So we may as well try and figure out what is the tension force. So we have Ft, magnitude of the tension force, sine theta, which is 30, but I'll plug that in a minute. I may as well just write it down. Sine 30 minus mg is equal to 0, because we are in equilibrium right now. Note that there is no acceleration happening. What I mean to say is there's no net acceleration happening. There is no changing of the forces on this in any way that has been indicated in the problem. So okay, so now we also have Ft magnitude cosine 30 minus the normal force in the x direction, right? Well, it's just the x direction only anyway. So okay, so we can use the y component and say Ft is equal to mg. Sine 30 is going to be 1/2, right? So that's 2 mg. Okay, great. So that's the magnitude of the tension force, right? And so now we want to find the torque. The torque is equal to R cross F. Okay, so, well, let's see what we have here. So now we have R. Oops, so we have R is going to be 1.75 meters, right? Our torque is being applied in this direction. Here is our R. Here is the force, okay? So Ft is 2 mg. Let's just do this. Magnitude of the tension force. Sine of the angle, right? Because here, let's do here, because this is from our previous vector identities, right? The angle is 30 degrees. This is going to equal 1.75 meters times 2 times m. Well, what was m? The mass we're given is 4.55 kilograms. 4.55 kilograms times g, 9.81 meters per second squared. Okay, sine 30 is 1/2. So this cancels, and this just leaves you with this these values here. And the units, Newton meter. So this comes out to be 78.11 Newton meters. So that's the tension. That's the magnitude of the torque. So that's the magnitude of the torque exerted from the tension force. Problem 80 says, consider the rod that we were just working with. What is the total torque around any point on the rod? Well, let's look at our diagram. What is the total torque on any point on the rod? Well, the only point that the force is actually acting upon is 1.75 meters out, right? So the rod is 1.75 meters. The tension force is pulling just at this point, 30 degrees with a 30-degree angle between them. So if torque is R cross F, then your total torque is just going to equal the torque that we found, 78.11 Newton meters at any point on the rod. I mean, because there's no force, there's no net force acting here. The force is pulling at this point, right? If there is, if torque is R cross F, and R is say 1/2 meter out, F is 0. Well, there's 0 torque here, right? From a 0 force, but there is a total force on the whole rod, and the total torque on the whole rod is 78.11. That's my answer. It's the same. That's what I'm trying to say. Total torque at any point is 78.11 Newton meters, because the force is only acting here. Problem 81 says, if the rod is in equilibrium, what is the tension in the rope at the instant shown? Okay, well, we already solved for tension earlier, so all we have to do is plug in the numbers and get the value, right? It's 2 times m times g. So what is that? 2 times 4.55 times 9.81 meters per second squared. This is in kilograms times kilograms, so this is a Newton. And this gives you a value of 89.271. So this gives you a value of 89.271. Say 89.27 newtons. That's the magnitude of the tension force. If we were intending to find this in vector form, then you would just take this sine 30 y hat plus cosine 30 x hat. That would give you the tension, the total tension, right? Which equals two values of 44.63 y hat plus 77.31 x hat. But actually, this is a negative value. It's negative 77.31 x hat. So if you look at this, it's pulling in this direction, right? Negative x hat. Also, it makes sense that this is greater force because it's pushing against this pole and it has to stay up. So, next problem. Okay, problem 18. We are given a situation with 4 particles connected by massless rigid rods, and they're rotating along the x-axis, around the x-axis. So if the x-axis is here, like this, this whole thing is rotating around that. So, what is the rotational inertia of the system around the x-axis? Okay. First thing we need to do is sum up the total rotational inertia. So, let's look at what that really means. I is equal to the sum of m of each mass times r squared, right? The general form, this is the more general form, but I mean, you normally would see it like this, mr squared, for point particle. Okay, since these are technically point particles, and they're just represented by larger balls because they're larger masses, right? But we're told they're particles, so we assume that they're points. Okay, so that pretty much means that we just multiply each mass by each radius squared. So we have 1 kilogram times 2 meters squared. Okay, 4 kilograms times 1 meter squared plus. So pretty much this just keep going. 2 kilograms times -2 meters squared. And then the last one is going to be plus 3 kilograms, running out of room, times 4 squared. Okay? So the total rotational inertia is going to be 4 plus, what do we have here? 4 plus 8 plus, we have 16 times 3, 48. So this gives you a value of 64 kilograms meters squared. Part B. So this was A, and this is B. Using K, KR is equal to half, what is this, I omega squared. What is the total rotational kinetic energy of the system? Okay, well, this thing is rotating with omega is equal to 2.5 radians per second. Let's do this. Let's make this highlighted so we can see it. Okay. Now remember when we did that merry-go-round problem, we found out that all of the particles had the same rotational speed, right? So, what is the rotational inertia of the system around the x-axis? So we just take the total inertia times the rotational speed, and this is going to give us 64 kilogram meters squared times, what was it, 2.5 radians per second squared. That gives us a value of 200 joules. Part C, what is the tangential speed of each of the 4 particles? Okay, well, let's recall that omega is equal to v over r, where omega is angular speed and v is your linear or tangential speed. We call it tangential speed, right? So that means that tangential speed is going to be r times omega. So for each particle, we're going to have, let's call this v1 is equal to, it's 2.5 radians per second for all particles, right? So this is going to give you, what did we say? That's times, okay, so times meters, right? So 2, and that's equal to 5 meters per second. So v2 is equal to 2.5 times 1. That's going to equal 2.5 meters per second. v3 is equal to 2.5 times -2, and that's equal to -5 meters per second. Okay, v4 is equal to 2.5 times -4, and that's equal to -10 meters per second. I think this will only be I mean, you're going to this is really magnitude, right? So we don't need these negative signs right now. Considering the system is 4 particles in motion and using k is equal to half the sum of half mv squared, what is the total kinetic energy of the system, and how does this compare with the result obtained in part B? Okay, so again, we just have to sum this up. So we just take half mv squared for every particle, right? So this is half mivi squared. That's going to equal, we'll just pull the half out because that's going to be the same for all particles. And so what do we get? Okay, so mass 1 is 1 kilogram. So we have 1 times V1 is 5. So 5 squared. And then number 2, we have 4 kilograms. So 4 times 2.5 squared plus V3. Number 3 is what? 2 kilograms times 5 squared again plus 3 kilograms. Just checking. Times 10 squared. Okay? So then we just add all this up. This ends up being let's just do it this way. Okay, so I'm not saying a lot, I'm just doing the calculation, and this ends up being 200 joules, which is exactly the same as what we found earlier. Okay, number 58, we're given a setup with two balls at the end of a rigid rod with length L. It says show, part A, show for the axis perpendicular to the rod here, the minimal rotation inertia of the system for an axis passing through the center of mass. Okay, so what it's asking us to find is we have to minimize the rotational inertia, right? Not too bad. Okay, so now let's start defining some things. Okay, so we're shown this. This is the center of mass, we'll say. Here is the axis of rotation, right? And so I'm gonna just draw this. So there we go. So what I've done here, this is length L, that was there before. We're just gonna call this distance between big M and the center of mass R. And then to keep this in terms of variables we already have, we're going to call this L minus R, right? This is L minus R. That's what's remaining. So we're going to use that. And now let's recall what moments of inertia even look like. For two balls, 2 particles, I guess this is what we would call them, 2 particles, we're going to have mr squared, right? Because this is this m and this r to the center of mass, and then we're going to have this m and this distance to the center of mass, right? So that's going to give us m L minus r squared. And so now to take a minimization, or I guess we could call these optimization problems, like from calculus, we take the derivative with respect to the changing variable and set it to 0, right, to solve for that changing variable. So r, in this case, is the changing variable, right? di with respect to the changing variable is r, and so that gives us 2 big M r plus 2, this is supposed to be little r, 2 times little m L minus r times -1. Right, and then we set this to 0 to find where r gives us that optimal value. So 2 big M r is equal to 2 little m L minus r. Right, we're getting somewhere. Okay, these cancel. Now we have m little r is equal to ml minus little m little r. Right. So now we have r big M plus m is equal to little m times L, which means r is equal to little m big L total mass. Okay, that's really interesting. So let's take a second before we move on to notice something. This looks like something familiar. So what happens if we find the center of mass, just given what we have, right? Remember that the center of mass is the sum of the mass times the particle's position, right, over the total mass. We'll call this mass net, right? So for our system, if we define this to be 0, so this is going to be m times 0, right, plus little m times L. This is L. So we're just going from 0 to L. Big M times 0, little m times L. That's going to give you the total center of mass. So let's write that out. Plus little m times L. This is over m net, and this is over big M plus little m. So the center of mass is equal to ml big M plus m. So that's the same thing that we just found by optimizing the rotational inertia. Isn't that interesting? So anyway, the point of this is the optimal spot for the perpendicular axis of rotation is the center of mass. That's what all of this means. So if you're going to pick a spot here for this thing to have inertia, then you want it to be the center of mass so that it spins with greatest efficiency, right? Part B says, what is the minimum rotational inertia of the system for an axis perpendicular to the rod? So what it's asking us to do, we already optimized for I net, right? So we found the minimum R, or we found the R that's going to give us the minimum rotational inertia, right? So what it's asking us to do is to take this equation and then follow it through and then plug in R min. So here we go. I1 plus I2. This is going to be mr squared plus L minus R squared. So just give me a second. Okay, I'm just trying to skip a few steps here and there so that I don't completely bore you with all of the algebra. So then, okay, so now we can actually pull out something that looks familiar. I'd say that we have definitely a value of 1 over m plus big M plus m, value of L squared, and a value of m. So what I'm saying is we can pull out a value that looks like this. Right, this actually, if we say that this is common to everything, then all we have to really do is a little bit more algebra to keep it simple. Okay. All right, we just have to keep following this calculation through. Now we just want to set this as the common denominator, so this will be multiplied by itself, and then this will be multiplied by this as well, and then we'll get that. Okay, so I just followed that through. This is what I'm left with. So we try this again. Pull this down. And now some things surely must cancel, right? So minus 2 big M little m, 2 big M little m right here. That cancels. I see a mistake. This should be little m. There we go. So okay. 2m squared, m squared, m squared. So that leaves us with not this, but this. 1 over big M plus little m. Okay, so now what we're really left with is this big M, M plus M, over M plus M. Make sure that I'm trying to make this clear. So obviously that cancels, right? And now, so here's what we're left with. So now we have little m, big M, L squared over big M plus little m. And that is the minimized rotational inertia. Okay, next problem, number 65. We're given a condition, or a situation rather, where there's a thin spherical shell and it's rolling down. So there's like half, it's a hemisphere, right? So it's going to roll down this side and it's going to slide up the side. This side is not, it's not able to roll. Let's get rid of these things. I was not quite ready for that. So it's not, so to make it a little cleaner, so it rolls down this side and then it slides up this side. That's what we're told in the problem. And so for a non-slipping condition, we have just these basic relationships that were given in the book, right? So again, rolling here, sliding here. We want to find out how high it's actually going to travel over here. How high is this thing going to come up here? It's going to roll down. How high are we going to get up here before it falls back down? Okay, so something useful that we can pull out of the book. There's actually a diagram. I forget which page exactly, but I believe it's in this chapter. That gives you a bunch of different moments of inertia for different geometries, right? So for a shell, the inertia is 2/3 mr squared. Cool. So we can use conservation of energy to start this. So we have two situations essentially, right? So I've kind of highlighted them as this, right? So we start here, and this is going to be like the end of that trip. Then it's going to start here, and this is going to be the end of that trip as well, of the next trip, right? So let's use initial energy here and final energy here. So what are we going to have? We're going to have mgh to start, right? There's no kinetic energy here. We're going to release it from rest. We do have gravitational potential. So we let this thing go and it starts rolling down. And then right down here, we're going to call this the end, right? Because we've run out of gravitational potential down here. So, but that doesn't mean that we're out of energy. That means that we've translated all of our energy. We now have half mv squared, right? This is our translational velocity plus the rotational, or sorry, what I mean to say is this is the translational kinetic energy, and then this is the rotational kinetic energy here, I omega squared. So that's a really useful thing. Okay? So we'll say that this is, we're going to relate this to right down here. How about this? Right? And then for the next side, may as well just kind of write this down. Now, because this thing is not, it's no longer rolling once it hits this side of the track, it's just going to have translational kinetic energy, not rotational kinetic energy. So that means that over here we just have half mv squared. Okay? And then up here we're going to have mgh. We don't know exactly how high it's going to go, but at some point it's going to reach a point up here where it has no more kinetic energy and only gravitational potential. And what we're trying to solve for is this h. So that's a pretty good start. So now we have, let's just mark these. Okay, good. So now we can start. EI is equal to EF, right? So let's just consider what we have. We have mgh is initial energy, mg big H, and then we'll say plus 0, right? next part is going to be 0 plus half mv squared, just like I had written down on the diagram up here, right here, plus half I omega squared. Okay, not bad. And remember that we've actually defined I, right here, our moment of inertia here is this for a spherical shell. So that's very useful. So now we are here, the mass times velocity squared plus half mass times the radius squared times omega squared. So one thing that we can do is we can actually break apart this rotational speed, right? We have a relationship, and remember we're told that this is a non-slipping condition. Over here, as this thing is rolling, there's a no slipping condition, and that includes, let's see, what do we have here? Pink. That includes this, which is something we can use. So V is equal to omega R. Remember that identity where omega is equal to V over R? Well, now we can take this and go omega is equal to, well, no, that's what we want, right? V over R. So now mgh is equal to half mv squared plus half mr squared, and now we have v squared over r squared. Okay, so now this cancels with this. Oh, it looks as though I have forgotten to write something down. I forgot to include 2/3 in my rotational inertia. So notice here, initial energy, final energy, I have my rotational inertia. This should be 2/3 mr squared, but I have neglected to write that down. Okay, so now we have 1/3. So now what do I have? I have half mv squared plus 1/3 mv squared. Okay, and that's equal to mgh. So now m is canceling because we're just talking about the same object the whole time. So now we have g times big H is equal to v squared 1/2 plus 1/3 is going to equal 3 plus 2 over 6 is equal to 5/6. Okay, now what that means is that this logically implies that V is equal to 6 over 5 g times big H all under a square root. That's what we have. That's the speed at which this thing is traveling as it goes down the ramp, and it's right here. Right before we hit the next part of the track, this thing is traveling at 6/5 GH under a square root. That's the value, right? So the reason I'm pointing that out so explicitly is because we're going to plug it into here, and then we can solve for H using conservation of energy once again. So now EI is equal to half mv squared on the second part of the track. We have no rotational kinetic energy, only translational. There's no gravitational potential, only kinetic, right? So this is going to equal E final, and that's going to equal only gravitational potential, right? Because I had mentioned that this thing's going to go up the ramp and lose kinetic energy and only have gravitational potential. Okay, so now that's pretty straightforward. So what this means is that H is equal to 1 over mg times 1/2 times m, so those cancel, times v squared, right? And v squared is 6/5 gh. So that means that g cancels, and okay, so this actually also cancels, that's 3/5. So now h is equal to 3/5 h. So that's the answer. That's how high this thing is going to go. So this thing here, we let it go, it rolls down, and then slides up here and goes about 60% of the way. and then it'll do something else like come back down. So that's pretty interesting. Next problem. So we're given a setup with a rod attached to a hinge, and there's a ball sitting on top of the rod. Okay, we're going to release this thing, and it's going to fall. So this thing is going to fall like this. Boom. All right. The rod length is L, and the diameter of the ball is D. Okay, and then we're given some other information here as well. Okay, so what we're asked to find, the rotational kinetic energy of the system when the ball and rod reach a horizontal position. So we want to find the rotational kinetic energy. So what is the rotational kinetic energy as this thing falls down? Right? Cool. I'm pretty sure this thing is just attached and this is not rotating. But the thing that is rotating is this, the whole thing together, right? So this is just kind of stuck up there and this is rotating together. All right. So if we just kind of consider basic conservation of energy here, we are going to start with pieces of this system in gravitational potential, right? As the rod, I mean, you're going to say that probably the center of mass of the rod is in the gravitational potential. So it'd be mgh, where h is the center of mass. Okay, that's what I would say. And then also this thing is going to have its own gravitational potential. So we can just take both of those and sum them up, which is probably the best way to do it. You could also determine what the center of mass of the whole thing is and then take your gravitational potential that way. Either way, you start out from a rest, there's no kinetic energy. This thing falls, there's kinetic energy, and then boom. So now there's no gravitational potential at this point. This is our 0 point. And we only have kinetic energy here. Okay, so what I'm saying is we start out with this, and then we go to, generally speaking, this. So, I mean, again, this is just the general form. So what I want to do is take potential of the ball plus potential of the, we'll call it the rod. I guess that's a good way to say that. And then, well, we need to find those separately, right? So let's do that. So gravitational potential of the ball. So the gravitational potential of the ball is actually going to be center of mass of the ball, right? So this is at 5 centimeters? So 5 centimeters plus L, where L is 15 centimeters. So that's 20 centimeters GH, right? So that's 0.2 meters times, what was it? It was 0.6, 5 kilograms is the ball. 5 kilograms times G, right? And then of the rod is going to be, so that's going to be 15 centimeters over 2. It's 0.15 meters over 2. That's the center of mass of the rod. This thing is 15 centimeters, so 15 centimeters divided by 2. That's your center of mass. That's where your gravitational potential lies. Okay, so that's going to be, that's H times M is 6 kilograms times G. Okay, so then what this is, I'll do it 2 methods. This is method 1, and then method 1 goes to, so you just add all this, you just do these and add them up, right? 0.2 times 5 plus 0.15 over 2 times 0.6. This gives you a value of 10.25 joules. That's what I got. All right, so there's another method that we could try. If you're not satisfied with that, oh, this is the potential, by the way. This is initial potential. And so if you're not satisfied with that, then we can find the center of the mass of the whole system. So remember that we do that by taking the mass times the position and then dividing by the total mass, right? So that's going to be, for this system, it's going to be 5 kilograms times 0.2 meters plus 0.15 over 2 times 0.6. Let's do this. 0.15 over 2. There we go. And then we divide by the total mass, right? 5.6 kilograms. And this gives you a value of 18.6 centimeters. Well, since I put it in meters, I'll just put it 0.186 meters. Okay, or 18.6 centimeters, right? So this thing is 15 centimeters long. Let's zoom in. This is 15 centimeters. So this is here is 0.2. So all the way up here is 0.2 meters. This is 0.15. So if we went 18 centimeters, the center of mass lies somewhere in here. Not quite in the middle of the ball, but a little lower. Hey, that makes sense. All right, and then so to find UI, we take, what was it? It was total mass of the system. Kilograms times 9.81, right? And then times the center of mass. And that gives you the exact same value of 10.25 joules. Now, so since we're starting here from rest, and this is just gravitational potential for the system, and then as this thing falls, we lose gravitational potential, and we have none at the final point for the energy, and we just have kinetic energy, the final rotational kinetic energy is going to be the same as the initial gravitational potential. We're not losing any energy. There's no work being done on this system. So this is going to equal the final kinetic energy, which is we can call this the final rotational kinetic energy as well. So that's the answer to the problem. Part B. Part B, it says find the final angular speed of the ball when they reach the horizontal position, right? So we have a value for kinetic energy at that point. We want to take half I omega squared, and we need to find I for this system, and that's probably the trickiest part about it. So I for a rod is actually going to be equal to 1/3 ml squared, right? So this is for a rod that's being pushed at the top. Like if it's being pushed here, it's going to be 1/12, but if it's pushed here, it's 1/3. And this is something you can look up. It's actually in the chart in the book, okay? So 1/3 ml squared. So that's the inertia for the rod being rotated. And then for a particle, we're modeling this as a particle, right, on top of the rod. For a particle, it's that's rotating around an axis. This is going to be mr squared, right, where r in this case is L plus little r, so that's 0.2, right? So that means that we have m, this is big M, L plus r, this is squared, so this is equal to 1/3 plus big M Well, I don't need to do this analytically because we have values for all of this, so we can just plug that in, and then I get 2.2011 kilograms meters squared. Okay, so that's the inertia for the system, and so we have 10.25 joules. We're going to take this to the other side. Remember that I'm using this equation. Now I'm just solving for the angular speed, because that's what we're asked to find. So I take this value here, divide by 0.2011, multiply by 2, and then take the square root of all of that. That's going to give me the value, and that gives me 10.09 radians per second. Radians per second. Which, if you divide this by, what is it, by 2 pi, that gives you about 1.6 revolutions per second, which is actually pretty reasonable for something that's just falling over. So I'd say that that answer makes a lot of sense to me. All right. What is the linear speed of the center of mass of the ball and rod when it reaches a horizontal position? So the ball is at 0.2 meters. We know that this is equal to 10. What was it? It was 10.09 radians per second. Right? And then that's enough to find what we need, because we take this times this, and that's our identity. So now we have 10.09 times 0.2, excuse me, times 0.2. That's going to be equal to 2.02 meters per second. That's the linear speed. I just used this to solve that, because this is a value we just found. This is something we have. Okay, and D. Part D. Consider a ball in free fall, 5 kilograms at 0.2 meters. Take the ratio, right? So if we want to find the speed, the linear speed for this thing, and so this is a ball in free fall, right? So it starts at rest, has just mgh, it ends with just kinetic energy, v squared. That means that these cancel, v, right? We've done this a lot of times at this point. 2g times 0.2, that's going to give you, if you plug that in, that gives you 1.8 meters per second. And then so you take the ratio. It says take the ratio. Take the ratio of part C to part D. What was it? So part C, we had 2.02 meters per second, and then part D, we had 1.98. This is a value of about 1.02, like that. Right? So this is v prime over v, as it's mentioned in the book.